And it looks like we're back. Good. Okay. So we are now looking at the header of a block. I might, before I go into that, scroll down a bit because there's all this stuff relating to the header. Here's the body. Here's the block itself. So the block is what actually gets submitted by the miners to get saved on the blockchain. Contains the header, contains a list of uncles, which are these are previous blocks that have been mined, but by people who are too slow. Ethereum takes these and includes them in later blocks and gives the people a reward anyway. I think the reward is like 25% less than what they would have got if they had have won it. So if you get like 10 Ethereum for winning a block, you might get 7.5 or something by submitting one that's one block late, or 2 blocks becomes half the value. I'm not fully sure. I've looked at the calculation, but I've forgotten it as usual. So Ethereum keeps these because the thought is that it still adds weight to the transactions if someone else has verified it, even if they weren't fast enough. It's been verified, so you're less likely to get a hacky, spammed, malicious chain if you're including people who are failing as well. And it also rewards people who are not quite as close and not as well connected. If you're in Australia, for example, the connection you're going to have to some of the main people in the main net is going to be a lot slower than what some of your American friends are going to be. So you're still going to calculate them, but you're not going to be able to submit them as quick. So it just gives room for these people to get some money out of it. So it encourages them to be on it instead of them giving it out, which builds power. Big list of positives as a result of it. Makes it a win-win for more people rather than being a sort of win or lose sort of situation. Header, transactions. Transactions are what, it's going to be a structure that's got just a list of transactions. Okay, so this body structure actually just mirrors it. As I say here, they don't actually use this body structure. It just makes it easier for moving around the contents. Because that's ultimately what's going to go into the chain, is you've just got a list of transactions, and then the miner's job is to build the headers and stuff. So the header is ultimately the most important part. The transactions are what you're sitting on your peer-to-peer network talking to people, and they submit all their transactions, which are whatever it might be, transferring money, creating a contract, interacting with a contract. If they get submitted to the net, you've got a big list of transactions you're maintaining on the side. That'll be in one of the other files we'll look at later. And the miner's job takes this, builds a header. There's other stuff here, like the total difficulty. So this is storing the difficulty that determines the nonce. Again, this calculation difficulty. So what is it? It's a big int, so just arbitrarily sized integer. And as you can see, that's the number floating up and down. It's getting easier. Let's, instead of do 1 month, all time, 6 months. Can I zoom out? From June 2018. No, Okay, give me 17. No, it doesn't want to go back that far. Coin Wars. Sex.io. Alright, so these guys are just make their own coin apparently. The Ethereum difficulty chain. Yep, this difficulty floats around 3. What's that? Some ridiculously high number. 3. And it has crashed recently down to 2. Much easier to mine. Not much easier to mine. It's still freaking hard, I imagine. It still only goes back to August. 30-day difficulty change minus 21%, 90-day minus 26%. That shows you how well Ethereum is doing right now. Cool. So difficulty is stored there, submitted to the block. List of transactions, list of uncles. You're going to get these from peer-to-peer. You're not going to be changing them at all when you're a miner. You would hope. You might select which ones you're putting in there because they're more or less valuable and have bigger transaction fees. But for the most part, you're just playing around with this header, specifically going through this nonce, which we were looking at before, incrementing it until the SHA, I want to say SHA 256, but it's not, but it might as well be, or SHA 3. Anyway, until the hash you make is less than the difficulty determines. Parent hash. So this header structure is probably the more important thing in this whole file. It is talked about in the yellow paper. And this is probably the standard. Everything you want with Ethereum comes really from this. Gavin Wood, big deal. If you look, there's going to be Vitalik in there somewhere. Where'd that search go? Yeah, it's got him with some of his papers in there. Big part of it. Anyway, the other paper, founder. So, what we've got in here in a couple pages is the transaction itself. Okay, that talks about the transaction. We won't look at that now. We'll look at that when we go through the file. But the block. Collection of relevant pieces of information, the block header, together with the information of the transactions. So you got your transactions, which are these guys, which have been submitted by people who want to interact with blockchain. There's a set of other block headers that are known to have a parent equal to the parent block. So that's a roundabout way of saying that they're headers of the previous block. Ommers. Which we're calling uncles now. I wonder what ommers means. Ommers. Google instead of DuckDuckGo, see if that does anything. Ommers. What is an uncle ommer block? Why are they called ommers? I go back. Why are they called ommers in this white yellow paper? They're called uncles now. Never used gender neutral term. the gender neutral alternative to uncle, aunt. The parent of a block is not. Yeah, cool. Okay, so you got the OMA, which is in the code itself, uncle. In the yellow paper, they're gender neutral. Good on them. So you got your parent hash. This is the previous hash. So when you're tying together all the different blocks, the way they're linked is the child references the parent. So if you go and say, where's my hash calculator? Something. And we calculate this hash. And we take this hash, which is the hash for something, and we put something else. Hash this. What we have here is a hash that references a previous hash. So if anything in this text box at the moment changes, this changes. Because that's the point of hashing something, is they're unique depending on what the content is, and they're collision resistant in that you won't get two hashes being the same without great difficulty. So the fact that this hash has the content of the previous hash means they're linked, and ideally you can reversibly traverse through them because you can find what the previous value was. So you take your parent's hash, you chuck it in there, so you're linking the new block with the old block, and that goes on right to the very first Genesis block, and that way all the blocks are linked. So you keep them linked. That's one of the defining factors of a blockchain is that it's a Merkle tree, that you have hashes that reference a previous hash. It's called a Merkle tree, hash tree. It's a tree where every leaf node is labeled with a hash of a data block, blah. I always think when it comes to mathematics in general, if you want to incorporate some form of information into another something, you have to incorporate it with a mathematical transaction. This is adding the variable of the previous hash to it. Uncle hash. This is a hash of the list of hashes. So it's not actually an array, but you've got down here below, you've got your list of uncles, your omas, and I think you're hashing that. That's what my understanding of that is. Where is the yellow paper? What does that say? Omas hash. The hash of the omas list in this block. Hash omas. So this is the hash of the uncles list in the block. And this is the hash of the previous block. Coinbase. This is how the miners get paid. You put in your Ethereum address when you mine a block. You're chucking in this. So it belongs to you. You say, I want to put my wallet into this block. And the result is the protocol gives that money, gives the Ethereum reward to that address. They call it the beneficiary here. So it's an address to which all the fees collected from the successful mining of a block will be transferred. Address to which the fees of the block get given, collected. Cool. So hash of the previous block, hash of your list of uncles, the address you want your money going to. Your block reward, the fees go to this address. And the protocol says whatever's there gets it. The root, this really is not very specific. It says state root here. But we look here and go into state root. And it references the state tree. And the state tree is what all the miners, all the clients maintain on the side. So the blockchain doesn't actually contain much information, but it contains a lot of information to verify some other information that's on the side. And this is called the state tree. In a blockchain, the UXTX unspent transactions UX unspent transaction outputs, that's what they're talking about. So in the Bitcoin blockchain, the state is really just a big list of unspent transactions. And that's it. It's just saying that there's a bunch of blocks that have allocated money to people, and these are the people who haven't spent it yet. And your wallet is just compiling as many of these as you can. In the Ethereum protocol, it's not quite as simple because each contract has a state, and it stores information there. And if you have a contract that's saying we are taking the votes from X amount of people, the state of that contract is what every one of their votes is. The blockchain as a whole has to maintain that state for every single contract on the blockchain. So it doesn't actually store that information because it's gigabytes. Size of the state tree in Ethereum. It's gigabytes. State tree pruning. World state. Understanding tree database. Go away. So there's a level DB database that you keep to the side. Blockchain state. Bitcoin state is a global collection of unspent transactions. One person has Bitcoin, transfers it to another person. The output says there's an unspent coin. In Ethereum, it manages account balances and all the contracts balances and all their votes and all the stupid shit, the crypto kitties that are on there. So the state tree is where all that garbage is staved. This is Vitalik's favorite data structure, a Patricia Merkle tree. And when you add information to the tree, it just means you can search it easily. WORD. WOOD, wood, right? Yeah, so you can search for it by going down each connection, each node, each connection as a reference. I don't fully understand myself. This is why I'm looking into it. It on its own is a pretty revolutionary concept, and that's graphing theory. They shorten it down to WORD, wood. So you store here the state of a contract, and the address of the contract is these connections down. So you go down, and I think they look at it a bit further, but it'll be in these nodes is the information stored in a contract. These links are all the addresses that the contracts are looking at. And when you've got millions and millions and millions of contracts, each with their own state down the bottom, pretty much every single one of these is going to be taken up. But the size of it is currently processing 1 gigabyte a month. So it's talking about garbage collection here for it. Yeah, so it's huge. So they don't actually save the state on the blockchain. What they do is they just have a hash of what it is at that point in time. So you're expected to build the state on the side by going through every single transaction. From the very start, you build up your transaction list. In Bitcoin, in Ethereum, it's a bit more. You go through every contract and you rebuild the state. And then once you get to the end, you verify that the hash of that state equals what's saved in the header. So you hash the state, which is just an object containing every contract, their variables, etc., and save it as a header. This is a big part of why the network is so slow for Ethereum, because it's a huge gigabyte sort of file to save the state, and rebuilding it is slow. So what they do is they often cheat and they don't start from scratch. They go ask someone who they think they trust and they rebuild it. And when it says they think they trust, there's a heap of I'm not going to say contentious issues, but whether or not you sort of trade off the risk of copying from someone who's been malicious. You obviously trade off the security a little bit for speeding up the transaction exponentially by, and I think they might go back 10 blocks or something, and then they check that the SHA equals it, and they might check a couple or something like that. I'm not sure, but the protocol really works hard on that, and that's what they're focusing on, because that's how they can speed up and get gains rather than fine with it. Next is just a hash of the transactions. So transaction to root, kekak 256-bit hash of the root node of the tree structure populated with each transaction. So down here we have a list of transactions. That is what has been submitted by people to go into the blockchain, and you do a hash of it. And what happens when you hash a list of transactions? So say in JSON or some data structure, you've got an array of objects, and you go name Sean, that's one object, name John. And that is a data structure. It is an array that has two objects in it. Then they're just the names. You might be able to shorten that, just say Sean, John, the comma. and that's saved as a JSON structure, right? And you can hash that. And the key here is you can hash absolutely everything, because the hash works down to the very smallest imaginable encoding of everything. So you can encode letters and characters as ASCII or whatever. You can encode data structures in some form of another. Mostly that's what marshalling is. You're saving, where's marshalling? Here they're talking about header marshalling. You're saving it to a string. You're taking this more complex object, saving it as a string, and that can be hashed that way. So anything and everything can be hashed, including a gigabyte file of Merkle trees, or a list of uncles, or this PDF would have a encoding. PDF is saved as a list of bytes in the end. You can take those bytes and you can hash that. And that's what people do. They hash PDFs. You can save that onto the blockchain, and that way you know that its content was saved at this point in date, and that's kind of how they doing the proof that it existed at this date. Especially if a blockchain consistently keeps time. So yeah, you've got your list of transactions. The transactions contained in the block is hashed and saved. And that's just to verify, like down the track, if someone was to change anything, like the hashes don't mash up. So you can't change anything, and that's the key, is once it's been saved there, you can't change anything. So the next thing is a receipts hash. And this is an Ethereum concept, in that when you code anything, you have the option to run a log command. And then Solidity, logging in Solidity, events and logging. So you can call one of these commands in Solidity, but ultimately it's a command that's in the Ethereum's bytecode. So you got a contract, event, log, coins minted. So in this case, he's saying that they made some coins, X amount, to an address, or you send some coins to an address for an amount. These are events that go into the smart contracts. And these events are designed so that this information is cheap and easily saved. It's not saved on the blockchain. It's just saved as a hash. But because it's contained in the state, then people can easily search these logs or events, or in this case, receipts. Because ultimately saving stuff on the blockchain is expensive. It's such a huge file as it is, and everything needs to be transmitted over the network, that the less you save on the blockchain, the better. So they've given this way of cheaply doing everything. For an exchange, these events are like a buy and sell event or something. And you can build software that will track this, and it will maintain, like it will watch over the receipts, and as stuff gets added, you can build your own calculations from the receipts that are coming out of these events. And you can log anything you want. And that's the point, is it's not restricting you. Blocks store transaction receipts, explanation what they are. Record the transaction outcome. So a transaction receipt has a hash of the block it came from, block number, address of the owner. Sorry, the logs, maybe I got that wrong. Yeah, so the logs are actually kept in this receipt object. So there's another layer. But every transaction that occurs on the blockchain is triggered by some form of transaction. So a transaction triggers a contract, triggers whatever. The result of the transaction includes some logs, which is what is in the Solidity one. Excuse me. So, you have the blockchain, you have a transaction being submitted. The transaction contains money being moved between an address, and every transaction has a receipt just to confirm what the result of the transaction was. So it records the transaction outcome. And what we have is all these objects, which are going to be described in another file, obviously. And in there is these logs, which I was talking about before. So I've jumped the gun, obviously, a little bit. State tree populated with receipts. So every transaction I have a receipt. I've seen some things in the code that says if they don't equal. So a transaction generates a receipt, which kind of conceptually makes sense. This includes a summary of what happened and if it interacted with a contract, what the result was. Logs. And then below it, logs bloom. And this is actually probably where the logs are kept. So a bloom filter is another complex mathematical structure, which I don't fully understand at all. My brief understanding is it's similar to a Merkle tree in that it just keeps track of stuff, and you can search it easily. And that's about my knowledge of it. So all the logs that are made from all the each log entry from the receipts is kept in a data structure. So all the logs are kept in this log bloom. The structure is just designed to make it easier to search. And the key part here is the indexable information. So you can search certain things by transaction ID if you determine that. But the contract actually allows you to state what is indexed, which makes it easier for people designing analysis software. Is you can, if they've set up a good index, then you can search through them. So all these logs kept in a data structure, not in the receipts data structure. That's a separate thing altogether. So all the logs in receipts are compiled into data structure. From this block. The data structure is sort of coming back to me now, actually. Bloom filter. Probabilistic data structure, yeah. I wonder if this would just give me a pretty picture of it or something. Yeah. It's just a way of saving space, enabling to hold many different items, and it gives you, what it does is it sacrifices accuracy in order to gain speed when you search it. So there are false positives. So you can search this data structure, you say, is this item contained in this data structure? And it will return yes or no and point you at it. The issue with this one is it gives you false positives, but it gives you faster searching for these items. So you're trying to search for a log. You can get false positives with this Bloom filter. Again, I don't fully understand it myself, so I'm not going to dig too much into it. It's on the list of things we're going to get our header in by the end of this. The difficulty is the big int of difficulty. What does the white paper directly say? Scalar value, so single dimensional value corresponding to the difficulty of this block. It's calculated by the previous block's difficulty level and the timestamp. So I'm not fully sure why this item is kept here and also here. So what's total difficulty versus difficulty? Versus pregnancy. Yeah. Versus difficulty in Ethereum. Difficulty and total difficulty. Ooh, here we go. It's literally asking what I want. So the current versus the accumulated sum of all the blocks, which is the best indicator for the longest chain. Okay, so if you take the difficulty in the header here, and you sum up every single block's difficulty, that'll give you total difficulty. So that's the point of that. And the total difficulty gives you the best indication of when there's a tie, which one should break it, because it determines the weight of the block chains. So if there's two chains that are competing against each other and you have to decide which one's more important, you want ways to establish why you chose one, and obviously the one that's more difficult has had more effort put into it, and therefore is a good choice to be chosen. So the difficulty of the current chain. difficulty. Current block. This is determinable from the previous block's difficulty level and the timestamp. So if the timestamp, if it got solved too quickly, it generally means there's more miners looking at the problem, so they up the difficulty. And this is one of those, like, the difficulty floats simply to keep the timestamp roughly consistent, which I think is 2.5 minutes for a block. Can I find that in here? Culti. So that's something that's going to be easy. Is defined as a smaller period between two blocks results in an increase in difficulty level. Additional computation is required. Lengthening the next one. If the period is too large, they'll reduce it. I don't know what the time stamp. Time of block. I think it's 2.5 minutes. Block in Ethereum. I don't see that in the white paper though. Average time block chart. It's going to be 2.5 minutes. No, 15 seconds. Ooh, September 17, it got to 30 seconds. That's when it got blocked. Look at that. Chunk, 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 chunk. 15 seconds. So try the average 15 seconds. Completely wrong. Etherscan.io. Does this give me last block? 13 seconds. Hash rate. Cool. Can I drill into a block here? Does that give me any information? Transactions for block. No. I want the header. Give me the header. That's the miner. This is one of the pools, obviously, it's huge. So, determinable by analyzing the previous timestamp and the current timestamp and increasing relative to getting 15 seconds. So without even knowing how they do it, digging into the mathematics of this paper, I would imagine that the difficulty increases proportionally versus how much it deviated from 15 seconds. So if it was 20 seconds, it's obviously a quarter, 5 over 15, what that turns out to be, 33% longer than it should have taken. So they'll decrease it 33%, and something along those lines. Don't know the exact, that's what we'll dig into later. Number, here we go. It doesn't actually say what number is, that's frustrating. What is number, you reckon? Number of ancestor blocks. Genesis block has 0. Number of ancestor blocks has 0. So that just gets incremented. And if we look at the Ethereum, it's going to have last block 6,800,000 hash rate gigas a second. Can I view a raw block? View all. Height. Like, give me a block. Here we go. We've got block information. Block number, parent hash, hash of itself, 135 transactions. Your list of your uncles. And extra data. Garbage. Uncle's reward. So the block reward is 3.08 ether for this one. So yeah, they just increment it by 1. Gas limit. So this is one of the more confusing things for myself. Gas limit. Scalar value, current gas limit. Gas limit in Ethereum. What is the value? So, gas exists to stop people from doing too many transactions on the blockchain. It's more expensive to do harder computations, and they charge you for it. How much gas a transaction will need? Blocks transaction gas limit. So that's the total amount of gas all the transactions are allowed to consume. So the miner sets the gas limit. It's something you set as a person. So it means that you can't, or you don't want to, put in thousands and thousands of transactions at a time. So you put a limit onto what you can. I'm not fully sure of why that's advantageous. So it's a miner set limit on how much gas is allowed to be spent by all transactions in the block. And I guess you set that in advance. So if I look at Geth, gas limit mining, will that give me anything? How to increase? Do anything. While I was advised not to alter the change gas limit, you can set gas limit here to this dude. Oh, fuck off. Has set it to 90. So many zeros. If we look at this guy here, he had 8 million. So that would be set by most of his. Let's have a look at that. So this guy's obviously mined more than a couple transactions. And here's, yeah, that's a transaction. Transaction. No, I don't want a transaction. I want blocks mined. Here we go. Oh, this dude's carving up. Look at that. You got 2. Who is it? Will this tell me who this address is? Comments. Here we go. So this Arxis Rich dude, he obviously just has like a ridiculous amount of ether on it. $600 ether. It's $60,000 at the moment. It's nothing compared to the billions. Anyway, so this dude has mined some blocks, and he set the gas limit here is 8,029, and it's the same there. Default gas limit Geth. Default limit. What is the default limit in gas limit? 8,029. So I guess that's the default set by Geth. You can change it if you want. It's set there as a protection to stop things. I think this is one of those ones where they were being spammed, like the chain was just being spammed, something shocking. So what they did was they dropped the gas limit to nothing, so that when it was being spammed, all these people submitting transactions just didn't get them through. Cool. So gas limits is set by the miner. Defaults to 8,029. Gas used. So after you've gone through all the transactions and executed them, you should know how much gas they used. Is the actual used gas. This should always be less than your gas limit, and if it was higher by its very nature, it shouldn't be accepted. It's like a faulty block that you should not accept onto the chain if the gas used is higher than the gas limit. The time. There's a big int of the timestamp. How is that stored, you reckon? Timestamp. Scalar value equal to the reasonable output of Unix time. Okay, so Unix's time is just a huge number of nanoseconds. So 2018 December 25th at 6:00. Convert. Days must be less than 31. 25. That's not Christmas. Yeah, so you get a number here which is 15, which is how many seconds have elapsed since 1970. So this is a big int, so it can increase exponentially. I think 64 bits, which goes to like year 200 billion or something ridiculous. So it's not going to get any of those Y2K problems that came up. So that just gets stored as a plain integer in there. Unix time seconds since 1970. Extra. I think this is, you can just put in whatever you want here. It's really like you don't extra data. So they're putting Ethermine AWS. Yeah, okay, so that's a mine input. So this is, you can put whatever information you want here. They've put that it's a pool. They got the AWS server in US 1.1. So it's got 50 tera hashes a second. And it just looks like it's carving up, doesn't it? This is huge. This is why there's so much issue with the miners, because these mining pools just end up too much control, which is a bit like index funds end up with too much control over the networks. So, what essentially is happening is you put whatever you want here. Miners discretion. Max digest. Mix digest. What do we reckon that is? Mix hash. Extra data. Arbitrary byte array containing data relevant. Less than 32 bytes. 32 bytes characters. I think it says 32. One byte, you get 32 characters. Cool. Mix digest. The 256-bit hash, which proves, combined with the nonce, that a sufficient amount of computation has been carried out on this block. There. What does that mean? Mix digest Ethereum. Ugh, so I can't even find it because which combined with the nonce that a sufficient amount of computation has been carried out on its block. So somehow these two are combined. Okay, so there's no actual hash in here of the block itself right now. So if I go back to Etherscan, hash. This has been determined somehow by the two here. Not sure yet. Nonce is incremented, mixed digest. Sounds like what's happening before you mix it with the nonce, but who knows? Cool. So that's all the items in the header. And what they do here is they give you the marshalling. So when you have a header, you can put it into a JSON common hash. So all that is to make it easier to save it as a string. My understanding is hash. So this So you take the RLP encoding of the heading. Now RLP is how they store, how it formally gets stored. So it's determining where all the bytes go, I think. RLP encoding Ethereum. Yeah, so you can take binary data and they encode it to serialize objects. So when you want to take anything and put it into a formal byte array, you obviously have an infinite amount of options as to how you save that, which is really determined by the person who is saving it. And Ethereum just uses RLP, recursive length prefix, and I think all it does is it just chucks so it takes an item and encodes it, and if it's a single byte, it will use that value. If it is a string, it'll save a number, OX80, and the length of the string. So if you've got if you've got a string that says, oh wait, do I have one? No. A string that's like OX blah blah did something, like whatever it is, that turns out to be an 80, a 0x67, 0x82. So it's a list of bytes. If you can imagine, those hex represent bytes. You encode them. If it's a string, it just chucks the length in here. So it'll go put 56 characters. And it just means that when you are a computer and you're reading this, you say, okay, this encode in here, 080, and then the length of the string, which means it's a string. If it is up to 55 bits. If it's more, it does some other stuff, and that way it says the size of the payload. It just makes it saving it into a byte array consistent. So when you do stuff like hashing, they don't change, because if you've got the same data, you want the same hash, and it would be a shame if you put the order of them in a different way, and as a result it ended up being hashed differently even though it was the same item, and you had a failed test because of it or something. So anyway, they take the header, they encode it into this recursive length prefix hash, which saves it to that and hashes it. I don't know if that's in here, RLP hash, yeah, there it is. So all it does is it takes, there's two functions down below it, actually right in front of me actually. It establishes a SHA-3 instance. RLP, it encodes the hash, and it adds it. So the way this works is you've created the SHA-3, you're passing that SHA-3 idea to RLP and X, which is a header. So RLP takes a hashing thing and some structure, which is in this case a header. So you say SHA-3 and a header, and it'll pass it to it, and then you add the actual data to it. And then the way that kind of works is every time you add something to this, it returns the hash of it. And a digest, in this context, you just add items to it consistently and it will return you the hash of it. So the hash gets done here. So you call hash on the header and it'll give you hash, which is exactly what the underlying matter is. bit more complicated. I don't fully understand it yet. That's why we're going through this. Size. This is a defined function by Ethereum, whoever made Geth, helper, to take the size of headings. Unsafe size of is built into the is unsafe in here? Is it imported? No. Yeah, it is. Here we go. What's unsafe do? Step around the type safety. So it will take the size of it, no matter what it is. Size. Returns the approximate memory used by all internal contents. It is used to approximate and limit the memory consumption of various caches. So it's just got a header. Let's calculate the size. You can hash your header, you can get the size of it. They're building in helper functions really here. RLP hash is simply wrapping the SHA and this RLP, which is defined by Ethereum, and that is yeah, I need to look into that further. Body block. We kind of looked at these earlier. Received at, received from. I think they're internal. Below here, they have some depreciated items by the looks of it. Depreciated total difficulty, which just returns the block total difficulty. Old relic for extracting the total difficulty, which is saying call it the proper way, or don't call it. They're going to delete it. If you want the total difficulty, which is saved in the block here, this will return it. They're obviously saying there's a better way of doing it, or not to do it at all. Another depreciated one. Storage block defines the RLP encoding of a block stored in the state database. Storage block just keeps a block. So these all look like helper functions for when they were building and maintaining the earlier versions. There's another storage block which contains a header, list transactions, list uncles, total difficulty. So they so instead of storing the block like it is up here, they had old databases and they saved them like this. I'm not sure which databases they're referencing, but obviously they've got a big list of databases somewhere or something that they wanted to keep originally, and they've got rid of. New block creates a block. By the looks of it, this takes everything. So it takes a header, it takes a transaction, it takes the uncles, takes your receipts, and gives you a block. It doesn't look like it actually does any computations here. It's just taking a bunch of information you've got. So you've built your header, you've built your transactions, you've built your uncles list. It's just chucking them in the structure for you. It doesn't actually do any computation. So, first up here is a to-do, saying they should panic if the length of the transactions does not equal the length of the receipt. And this is what we were kind of looking at before. They have a receipt for every transaction. So you submit a transaction to go on the blockchain. it has some consequences on the state. And it also, if it's interacting with a contract, will give you some logs, and it will give you some other stuff. Not fully sure, it's on my list of now, we're going to review it further. If the length of receipts do not need transactions, it should panic, they haven't implemented that yet. In this case, if you give this function transactions that are nil, that have no, an array with nothing in it, it'll give you an empty root hash, which is those functions at the very top that is helper functions. If it does have transactions, it is putting them into transactions file, so this data structure, which is interesting, and it gets the SHA of it. SHA-3, but it's not SHA-3, it's KK. So let's have a look at that. SHA-3 versus KK. So SHA-3 is the latest member of the hashing standards, released in 2015. This was after Ethereum was done. It's a subset of a broader family called KK. So this is standardized by NIST, but I guess everyone knew that KK is a good one. Ethereum being released before this was finalized probably made an executive decision to use this. That's why. So they call it SHA even though it's not, but it is, because it's the same family and it's probably similar in 99.9% of the ways. Make transactions the length of transactions. So the transactions is the list, and you copy it into there. If the receipts are empty, you get the empty one. Then they generate the SHA from it, put it into its own data structure. They create the bloom. So they go through all the receipts to get the logs, and they create the bloom filter, the weird data structure. They go through the uncles. Same deal. If there is an uncle list, they'll calculate the hash. If not, they'll ignore it. It must have its own thing because it's special. New block with header. This only takes a header and makes a block. So this copies it. So they're going to an effort here to copy it rather than put it directly in there. So when you've got data saved on your computer in memory, so your program has memory on the RAM, and somewhere in that big blank open cell of RAM is the header where it's been saved. Now, when you create a new block, you can, the way the RAM might do it is point directly out to that existing header. They're saying they don't want to do that. They want to create a new header in a different place in the memory and use that new one in there. And that means that when there's changes, it will not affect the block. Yeah, they create a deep copy to prevent side effects modifying it. So it's just a risk. And I guess here there's probably the things that are key is they're looking at the time. They're making sure it's set. If not, it sets the time. H time header.time. Copy.time.set. So there's a function on the time set. Time is a int. It says int set. Golang int set. No, that's not what I'm set as in like set theory. Nah, not it, not it. Cool. So deep copying, they set the time if it's not. They set the difficulty. Nah, okay, cool. So in the new copy, they're making sure the time equals what was in the old header. In the difficulty, they make sure it equals that. The number, they make the same. Extra. Copy extra. What the fuck is extra? I guess that's everything else. Not fully unsure the purpose. I'm assuming that, yeah, you got memory. Something changes underline it from another function because it was pointed there instead of copied. There's risks of damages. Decode RLP, decodes the Ethereum. So RLP stream is that recursive length prefix. So you got a byte array that's been encoded specifically in this Ethereum, not proprietary but open source standard. You can take that and it will give you a block. So they're creating this extra block, which is a ext block. So why is that not? No, there it is. Yeah, this is their weird. So they got 1,000 different data instructions for the block. Some are used for block encoding. Some are used for their databases. The main one here is what they use for the actual protocol I'm running in Geth. So when you go to RLP encoding, it just gives it a nice convenient data structure to save everything in before, and then they move it from this external block into the actual block later on, I imagine. Or it might not even be that. It's got the external block's got all the information in it. You can call this new block header here, the function here, and pass it, the header, the transaction uncles, which is what's contained in this header block here. Header block, external block. Cool. So you got a decoding stream. A stream that's saved in a weird proprietary Ethereum structure. You decode it into EB. That's obviously a function of a different package. So we'll have to look into that later on. And then you get the size and it just builds it. Encode goes the other way. So it takes something that's in that external block. Doesn't even take it in external block. It just uses that in reference. So you take your block, which is your normal block. In here, it builds this external block by putting a header, the transactions, and uncles. So it's formatted in a nice way that it can pass to this RLP encode. And the writer is a file or something. So when you write to a file in Go, you need a writer. So you open the input file. You got your byte array. you read from the file into the byte array, into the buffer. And when you're doing it the other way around, you write into it. So the buffer is your writer. And in here, you're passing that buffer or whatever you want to write it into. So you make it just a weird byte array or something that you're going to save to a file. Pass it there. And it will put the block into its weird little form, encode it, and chuck it here. They've got some depreciated stuff. Decode RLP for storage block. So the same deal. Their storage block is their database structure. It's a block, but it's phrased a little bit. They got to do for copies. Here, if you've got a block, call the uncles. It returns you the list of headers, and one-liner gives you b.uncles. So right now it's just going through the helper functions on a block. So if you've got a block saved over here, say it's come as a block, X is your block, you can call .uncles or .transactions or .transaction and give it a hash, and that will give you everything that it needs to be able to program around. I imagine this is going to go through everything that's in there. So you got the number, so block height, the gas limit, gas use, difficulty, time, blah, nonce, bloom, coinbase, parent, transaction hash, ETH hash, extra, and the header itself. So, you know, it's going through all these items. So if you've got a block, you can just call parent hash, and it'll give you the parent hash somewhere, I imagine, parent hash. Not beneficiary because it's called Coinbase here. Or you want the header, or you want the body. And the body isn't even used in a block, so it creates this new structure which has just the transactions and the uncles, just in a convenient data structure for you to look at if you are doing that stuff. Size returns the actual RLP encoded storage. So the other one gave you an estimate. This one gives you the actual one of the RLPs. And of course, as you if you encode things differently, they're going to be saved differently. So like if you've got a text file and it's saved as ASCII and it says whatever it says, it's going to be a different length to if you save it as UTF. So especially if you save it as a bigger one that had Chinese stuff in it. Write counter, common storage. Calculate the uncle hash functions. Okay, so and again, these are sort of things that have been tacked onto the bottom to make your life a lot easier when you've got a block. Returns a new block with the data from B. Block with seal. Copy equals header. Returns a new block with the data from B, but the header replaced with the sealed one. So what I think's here is you're doing all your calculations, but your header isn't finalized yet. But you've got a block and it's half done. So you take out the header, you do what you need to do with it, and you create a new block using the same transactions and uncles. And it's got the header information you'll pass into this. This does the opposite. If you've got the header and the transactions that have made changes, again, I don't see where they needed to do this yet. Like, there's obviously been called somewhere, and they've needed to replace the body into a new block without changing the header, and vice versa. You need to change the header without changing the block. Hash. Okay, cool. So you take the block and you hash it. It returns you common.hash, which is a Golang structure. Hash equals the load. So if it's already got it, it returns it, converts it to a common .hash, and then it saves it. That's where it calculates it. It returns that. Computed on the first call, so it's just calculating the hash. Type blocks is an array of blocks. Block by function takes 2, returns a bool. Self block by sort. Okay, so there's defining a way to sort blocks. Block sorter. Blocks block by self. Block sorter takes blocks by. So it's passing itself. So you've got all these functions less. I imagine there's a greater than somewhere as well. And you can call this block sorter method give it 2 blocks or an array of blocks. Give it this less function here, and it will sort it and make it, and it will return whichever one's less. And these are all tools to give you some way to compare blocks. So you've got the length of the block, returns length self to blocks. Block sorter. So this is how many blocks you've got in there. Swap. So these are really just giving you the ability to take a list of blocks. So blocks, which is a list of blocks, and you can sort them. Self blocks I, self blocks J, self by. Number. Block 1, block 2. Block 1 header number compare to block 2's header number. It's greater than 0. So they're comparing it. Less number. If the number is less. So can I find that? Where is it calling that? The header number. No. So they finalize it by saying that you can compare blocks by going through, and if the head number is higher than lower. So if you've got if you've got here the height of this, that one's obviously higher than 6863803, but a computer can do that for simple numbers. But in a block, if you give them 2 blocks and you say which one's bigger, it'll go, I don't know, unless you define, which is what they've done here, that I want to compare them by block header, not by their hash or something arbitrary. And that is the end of the block file in Ethereum. So, as you can see in here, quite a few transactions. I've got exit. cd did it. In here, I got a list of the files, and as you can see, it's quite a big. I deleted the first ones, but 2,770 files. As you can see, a lot of it is. That's the Whisper. 50 files there. Vendor. Say we're not going through the vendor stuff, so we'll ignore that. And this is probably actually going to be thousands. So we're going to ignore the vendor stuff because they are libraries that the Golang references, and it's not actually part of the Go Ethereum client. So once we get rid of these, we'll see how many files. But the aim is to go through essentially everything in an effort to teach me what's actually evolved in the protocol. I know quite a lot of work is going into the Ethereum protocol right now, and they're trying to release all the stuff with the new proof of stake and getting that to work with they got the Ghost protocol, and I think there's two. I don't fully understand them yet either. So it might be a bit waste of time going through it now, because in the next few months there's probably going to be some changes, significant changes. But I feel like it's good to get your head around. And eventually I'd like to contribute some stuff to this. But we need to get fully around it. Yeah, look, there's already 1,000 files in this vendor file. So we'll get rid of that. And yeah, eventually we'll go through them all. Blocks is obviously the big one, why we started with it. And if anyone has any requests that they want, tree. Done. Delete. 1,200 files. Tree. Oh, there's tests. We're not going to go through the tests. What are we going to get? That's only like 10 of them. Bugger. Not much savings there. Swarm is a way for storing information using the protocol, but not on the blockchain. So it is. This is what's up with Ethereum, is they've developed things like Swarm and Whisper, which is like Swarm for storing information, Whispers for messaging, using the protocols they've developed, but not actually on the blockchain. So it's not exactly relevant, but it's interesting nonetheless, because they use the same underlying protocols. They've obviously here they've devoted a lot of files to peer-to-peer, each nodes, mobile. I know they're making a lot of effort to make smaller light clients, because you obviously in the end want it all on your phone when you're paying for stuff. Some logs, the light client, Les, I forget what that's called, Les Ethereum, Light Ethereum server. Light Ethereum sub protocol. It's used by the light clients. And internal events, the database. They use a level database underneath it all, so this is mostly just wrapping convenient functions. The ETH client itself, the protocol. You got a dashboard, which probably is not very useful. Crypto, they I think actually roll some of their own crypto here, which is interesting. In C, I might have just downloaded it from someone else, to be honest. They got their virtual machine here, so that's a big part of it, the Ethereum virtual machine. types. So this is where we were. We have now looked at block.go. I'm going to say done. So this is the state tree, making sure they sync it with it, the raw database, Genesis test, Bloom bits, blockchain, contracts. I think they got some default contracts in here. So there's a Solidity contract. So these contracts I don't actually think are part of it. They're just giving you examples of contract. So they give you a checkbook, and they give you a register, public resolver. I don't think anyone uses it. Etherhash, consensus algorithm, proof of work. So when you mine, this is what's being done. Click is for the test net. It's another consensus, so they take out ETH hash, so you don't have to do proof of work over the test one. They just make it a bit easier. So when you're doing private networks and testing and all that stuff, you don't actually want to do calculations of proof of work. You want to see if everything else is working. So they got this easier one that's haven't dug too much. They got some math stuff here. They got hex utilities. Of course, they got some utilities. Command is where all the command line stuff comes in. So this is how you would call the swarm client when you go Geth swarm, Geth puppet, which makes private servers for you. Like, cause setting up a private server is sometimes a pain in the ass, and what you need like wallets, and you need Ethereum faucets, and you need stats, and that's what all these ETH stats. So you want all this stuff on your own private networks when you're making them. So they give you all the ability to do so. Geth is the main command line that does everything. Faucet, ETH key generates keys for you. Clef, not sure about. Build stuff. So this is all building it with make build. But I think Go, using Go build is the main way of doing it. They just give many options. Accounts, so this is managing your keys. Application binary interface, not sure what that's doing in accounts at the moment, but all pretty important stuff. So that's where I'm going to call it for today. And we'll start going through some of the other stuff tomorrow.